Hello, everyone. My name is Babis Tsourakakis, and currently I'm a postdoc at Harvard University. I'll be joining Boston University in a couple of months as an assistant professor. And today, I'm going to specifically talk about a key graph mining challenge known as dense subgraph discovery. And I would like to start by giving a few motivational applications. So suppose that you're given a large who calls whom network. This is a network where every node is a human, and you have an edge between two humans if, let's say, they exchange at least one phone call. So a problem in which many security agencies and telecommunication companies are interested in is finding large sets of nodes which are not necessarily fully interconnected, but they're what we call large near-cliques. They're not necessarily cliques, but they're very dense. We're going to see mathematical formalizations of this later, but intuitively you can understand why this is the case, why this is of interest to them. It's because of interest in anomaly detection. How many of you, for instance, know 100 other people who all roughly call each other, right? It's something that deviates from usual human behavior. So it's being used for security reasons in anomaly detection tasks. Nowadays, we have a lot of social media data. And here's one application using Twitter data. So you have tweets, and then using natural language processing tools, you parse the tweets into entities, and you can create a graph where every node corresponds to an entity, and you have an edge between two entities if they co-occur in the same tweet. So it turns out empirically that if you find large near-cliques in this kind of co-occurrence graphs, they tend to have some sort of thematic coherence. So for instance, this kind of large near-cliques can be used to find interesting stories that haven't been hashtagged, for example. We have a lot of genomic data nowadays, and here's one application that has to do with large near-cliques in computational biology. So computational biologists, one of the data sets deal with are microarray data sets. So you may have several human subjects who have cancer and several probes / genes. So they create a graph where every node is a gene, and you have a connection between two genes if their expression profiles across the list of human subjects are somehow similar, okay? So this notion of similarity depends on the choice of the similarity measure, maybe correlation coefficient or other correlation measures, but the key thing is once you have this network and has been created in a good way, if you find large near-cliques, they tend to correspond to sets of genes which are functionally related. And this is important for designing therapeutics for diseases like cancer and other kind of diseases. So today, this is outline of my talk. I'm going to present a subset of results that appear in 3 papers. So first I will start with a short, brief discussion of related work. Then I will discuss a new objective for finding large near-cliques that leverages motifs. I'm going to show you 2 applications, and then I'm going to care about scalability. So we're going to see that this novel objective, it succeeds in practice in solving this NP-hard problem of finding large near-cliques, but we have to pay for something. And then we're going to design some randomized algorithms. This is a theorem, the Densest subgraph sparsifier theorem, that is going to allow us to scale this computation to really large-scale networks. And then I would like to state a result from, let me say that this appears in the KDD paper, which is joint work with Michael Mitzenmacher, Richard Penk, Jakub Paczocki, and Shen Chen. And then I'm going to state the first result for finding dense subgraphs in time-evolving networks with solid theoretical guarantees and a new line of research, which I believe is of interest to other graph analytic applications as well. And this is joint work with Monica Henziger, Danu Ponnanonkai, and Sayan Bhattacharya, and appeared last year in Stockholm. And then I'm going to conclude with a few future research directions. So let's start with some possible formulations of finding dense subgraphs. So if you have a set of nodes S, a very natural measure of density is the H density. It's essentially the probability that if you pick a random pair of nodes, they're connected by an edge. So this quantity, let's call it Phi of S, is equal to the number of edges induced by S, so both endpoints of the edge are within the set, divided by S choose 2. And it's a number between 0 and 1. It's 0 if it's an independent set. It's 1 if it's a clique. So you may ask, why don't we try to optimize this notion of edge density? Well, it turns out that this is ill-posed. It's problematic. And the reason is a single edge achieves the maximum possible edge density. As you can see, it's 1. So as soon as we try to save ourselves from this problematic situation by adding some sort of cardinality constraints, the problem becomes NP-hard. And not just NP-hard, it's really hard even to approximate, because it's connected to the maximum clique problem or the k-densest subgraph problem. So the approximation guarantees are kind of, we have to allow for really large approximation guarantees. And this is not nice. So let's try another possible formulation. We're going to define the notion of degree density. So for a set of nodes S, we're going to define rho of S to be the number of edges induced by S divided by the cardinality of the set S. So for instance, if this is our toy graph and S is the green set of nodes, then we have 5 nodes inside here, so the denominator is 5, and we have 7 edges, 6 from the clique plus this one. So the density of this thing is 7 over 5. It turns out that this objective can be solved in polynomial time. And this is known since, I would say, the 70s, and definitely since the early 80s. So there's a series of papers by Goldberg, Gallo, and Kuller who show efficient algorithms, exact optimization algorithms for this objective. Besides those exact approximation algorithms, we have an efficient two-approximation algorithm. So you may ask, why do we need an approximation algorithm if we can solve the problem exactly? Well, it turns out that the two-approximation is very, very efficient. It runs in linear time and uses linear space. So n is the number of nodes, m is the number of edges. This problem here is known as the densest subgraph problem. And as a problem by itself is very important in many different applications. But in the context of trying to find these large near-cliques, it fails. And I'm going to explain the next slide. I'll give you some intuition why it fails. But, so this is I'm quoting a paper by Bahmani and Google researchers that say that this problem lies at the core of large-scale data mining. But unfortunately, if we try to add cardinality constraints to this problem, the densest subgraph problem, in order to avoid the issues that I'm going to show you in the next slide, again, it becomes NP-hard, and again, it's really hard to even approximate. So let's see what happens in real data and this objective that we understand very well and we can solve very efficiently in practice does not succeed most of the times in finding large near-cliques. So this is a small graph with 150 nodes and roughly 600 edges, which correspond to teams and games between them respectively. Well, if you solve the densest subgraph problem on this toy network, on this small network, it turns out that the optimal solution is the whole vertex set. Okay, so this is not very informative. So it turns out that the optimal degree density is 5.3, which is the number that you get if you divide m by n. But the edge density that we care mostly about is really close to 0, okay, because it's a very sparse network. At the same time, in this graph, there exists a set of 80 nodes with edge density 0.48. But we cannot find it using the densest subgraph problem because the degree density is smaller. So this is what happens in large-scale networks in a more pronounced way. Somewhere in your graph, there exists some sort of large near-clique, some sort of anomalous cluster that you care about finding. But if you try to use the degree density measure, it's hidden. Because you tend to find large sets of nodes which tend to be sparse and have low degree density. So how can we find these sets that we care about? Before going into our contributions, I would like to quickly say something about the streaming model for those not familiar with it. In the streaming model, the graph appears as a stream of edges. We don't assume anything about the ordering of the edges. It's an arbitrary ordering. And this computational model has the following aspects. So we can have insert-only streams versus dynamic streams. In insert-only streams, you can only have edges coming in In dynamic, you can have additions and deletions of edges. The model is really strict about the available space. So we have n polylog n bits in total. This polylog n factor is hidden by this tilde here, instead of having linear space, which is n plus n. The model cares about minimizing the number of passes that we do over the stream of edges. Ideally, we would like to do one, but in many cases, we either don't know how, or we even have lower bounds that we cannot do it within constant number of passes. And we would like to have as good approximations guarantees as possible. So for the densest subgraph problem, prior to our work, the state of the art was due to Bahmani, Ravi Kumar, and Sergei Vasilvitsky, and work for insert-only streams, uses n polylog n space, perform log n over epsilon passes over the stream of edges, and achieve the 2 plus epsilon approximation. So we're going to improve this by giving an algorithm which achieves a 1 plus epsilon approximation using a single pass. So it's essentially optimal. Okay, so let's go to the large near-clique detection. So I would like to define the k-clique densest subgraph problem. So for any set of nodes S, let's define Ck of S to be the number of k-cliques induced by S. So a 2-clique is an edge, okay? This is a click on 2 nodes. A 3-clique is a triangle. So let's define the k-clique density to be the number of k-cliques induced by S divided by the cardinality of the set. So this is nothing but a generalization of the densest subgraph problem, which I showed you a couple of slides ago. When k equals 2, it's exactly the densest subgraph problem. But the intuition here is that as we increase k, for instance, if we take k equals 3, triangles is a much better signature of community participation compared to edges. So if you have three people, A, B, and C, and A is a friend with B and friend with C, then the probability that B and C are friends is way higher than if B and C were 2 random people on the street. So the k-clique densest subgraph problem is the following. Maximize this notion of density over all possible subsets of nodes. So the 3-clique DSP, I'm going to refer it because the special case has a triangle densest subgraph problem, and this is a notation I'm going to use. And we have to answer a few questions about this generalization. The first thing is, how different can the densest subgraph be from the triangle densest subgraph, and more generally from the k-densest subgraph? Well, in principle, they can be radically different. And this is very easy to see. If you take the union of a bipartite graph and a triangle, the densest subgraph will give you the bipartite clique. The triangle densest subgraph will give you this thing as the optimal solution, simply because in bipartite graphs, we don't have any triangles. So the interesting questions here is what happens on real data and whether we can solve this generalization in polynomial time. So here is first theorem. We can solve the triangle densest subgraph problem in polynomial time, and specifically the algorithm that I have in the paper is m to the 3/2. M is the number of edges, n times t, n number of nodes, t the number of triangles, plus the minimum of these two quantities raised to the cube. And furthermore, for any k constant, we can solve this problem in polynomial time. The computation involves 2 steps, and I'm not going to elaborate on this. We enumerate the set of k-cliques, and then we solve a maximum flow computation on an appropriate network. So this is going to be, the maximum flow computation is going to be the key computational bottleneck, as we'll see from our experimental results. What I would like to elaborate is the very interesting behavior that we observe on real data when we solve this generalized version of the densest subgraph problem. So what I have in this slide, this is the results that we obtained for the Epinions social network. It's a graph with roughly 75,000 nodes and roughly 405,000 edges. You can see here in the table the number of k-cliques for k3, 4, and 5. You can see their counts, and you can see the number of seconds that we need to actually enumerate all of them. Okay? So now, the interesting part is this behavior that we see here. On the x-axis, you can see k. Okay? So k is a parameter of the k-clique that we're optimizing for. And on the y-axis, it's the size of the optimal solution. So for k equals 2, when we solve the densest subgraph problem, we find that the optimal solution, the optimal set, has roughly 1,000 nodes. You can see that the dots have different sizes. So for visual convenience, I've scaled the dots proportionally to the edge density. So the closer the set is to being a clique, the larger the dot. Okay? So what you can see here is that for k equals 2, as I said, the optimal set is roughly 1,000 nodes. The edge density is roughly 0.12, and we can actually find the set in roughly 2.37 seconds. And these experiments have been performed, let me say, using Goldberg's high-performance max flow code on a simple machine, like this one here. So as we increase k, what happens is the edge density increases, and the output size decreases. So when we solve the densest subgraph problem, we find something which is far away from being a large near-clique, but as we increase k, we end up finding for k equals 5 a set of 172 nodes with edge density 0.5. And you can see this pattern, which actually appears in a wide variety of data sets that we tried, not just social networks, for which I had this original intuition about. So the cost that we have to pay is that the runtime for k equals 5 is really huge. And this is because the number of 5 clicks explodes, okay? So solving max flow on this network takes roughly 38,000 seconds. And this is really bad. But the nice thing here is that if you are a practitioner and you care about finding these large near-clique sets, this is a principled way to go about this problem. Instead of trying different tools that exist around, hoping that one of them will work, or maybe heuristics that you don't have guarantees about, this thing gives you a principled approach to attacking this hard problem on real data. And in the next slides, like later during the presentation, we're going to see how this runtime can be sped up several tens of thousands of times using sparsification. So here are two more networks, just to show you that the same pattern appears not just in social networks, but in collaboration networks, email networks. You can see the number of nodes, number of edges here. You can see that for the astrophysics collaboration network, we can find that the densest subgraph in roughly 1.2 seconds. It has edge density 0.09, but by increasing k and going to k equals 5, we can find a set of 62 nodes with edge density 0.96, which is essentially a clique. Okay? Same thing with the email network. So this is very interesting, and one open problem here is, can we explain this type of behavior on real data using some sort of random graph model? Because this behavior is definitely not the case on all graphs. For instance, if you take Erdos-Renyi graphs, you would see something which is flat, instead of seeing this behavior. So let's see a couple of applications of using this tool. So I got the patent citation network for a period of 37 years. And for every year, I computed the densest subgraph and the triangle densest subgraph. So with blue dots here, you can see the density of the densest subgraph, and with red, the optimal triangle density. And you can see that it explodes. If you see, however, the total number of triangles and the total number of edges as a function of time, the number of edges grows faster than the number of triangles. So this suggests that the edges are being placed in some localized way, and they create some sort of large near-clique. So it turns out that what was happening here, there was a company called Allergan, it's a pharmaceutical company, that every time it was publishing one patent, it was citing all of its previous patents. So you could find a large near-clique around this pharmaceutical company that if you remove from the data set, then the red dots flatten out and look like the blue. One family of applications, especially important in biological applications, is what we call the cocktail party. So suppose that I want to organize a party and I want to invite Jimenk and David. Who else should I invite so that the party would be successful? Okay. So assuming edges are a notion of friendship and similarity between nodes, we can formalize this kind of cocktail party as maximizing some notion of density, let's say the triangle density or the k-clique density, subject to the optimal set S should contain the query set Q of nodes that we care about. And we can solve this in polynomial time. Again, for the details, you can see the paper and some indication of what we see on real data. If we take the DBLP dataset, Christos Papadimitriou is a prolific author in different kind of communities, databases, theoretical computer science. Well, if you set Q to be Papadimitriou and search Abitaboul from databases, you find database people. And similarly, if you set Christos and Manuel Blum, you find theories. Okay? So let's see now how we can speed up things. So I'm going to discuss about sparsifiers. And the notion of sparsifier was introduced by Banksquare and Karger in 1996 in the context of cat sparsifiers. The idea is very general, though. So you have a graph G. You care about some graph statistic. And what you want to do is you want to sparsify G to get a much sparser graph H that if you do your computation on H, you can give some solid approximation guarantees about the graph analytic on G. So there exist different notions of sparsifier, cat, spectral. I've done some work on triangle sparsifiers. Today I'm going to talk about densest subgraph sparsifiers. So I would like to make sure we're on the same page. So let me define the notion of a hypergraph because I'm going to give a very general theory. So a hypergraph is a generalization of a graph where we allow any number of nodes to be connected by a hyperedge. So this is an example of a hypergraph here. You can see this yellow hyperedge. It connects 3 nodes rather than 2, which is a usual notion of a graph. So our theorem says the following. If you take a hypergraph H and you have some accuracy parameter epsilon, then if you take a sample of edges, of hyperedges, uniformly at random, such that the cardinality of this set is n log n over epsilon square, actually 6 n log n over epsilon square, we have the constant here, then if you solve the densest subgraph problem on this sketch, on this sample, you get a 1 plus epsilon approximation to the densest subgraph problem on the original hypergraph. You may ask, why did I discuss hypergraphs since I've been discussing about graphs all the time? The reason is the k-clique densest subgraph problem is essentially a hypergraph problem. So for instance, if this is my graph here and I care about the triangle densest subgraph problem, well, I enumerate the triangles, and for every triangle, I add the hyperedge. So the implicit hypergraph that corresponds to this problem is this thing here, where we have 2 hyperedges corresponding to these triangles here. So the technical difficulty behind this theorem, the densest subgraph sparsifier theorem, is the fact that Chernoff gives you a failure probability of 1 over a polynomial, n to some constant d. But the number of bad events that you have to consider is exponential. So you have to do something refined, and turns out that if you take a refined union bound, things work out. The intuition is that as the size of the set increases, the failure probability decreases as a function of the size of the set. So you can take a refined union bound over all possible cardinalities of I from 1 up to n, and you have this type of union bound. And by choosing the constant here, you can make this go down to 0. The important thing here to remember is that, as I said, for the k-clique densest subgraph problem, in theory, the number of k-cliques can grow as n to the k, right? So what this theorem says is that you can downsample the number of k-cliques that you have to n log n over epsilon square and still get a really good approximation to the densest subgraph problem. As a corollary, direct corollary of this sparsification result, you can get a 1-pass streaming algorithm that gives you a 1 plus epsilon approximation. The technical details for dynamic streams, you can find them in the paper, starting from our stock paper. But the idea is very simple. You have the stream of edges. Suppose it's an insert-only stream. The only thing you need to make sure is that at the end of the stream, you have kept n log n over epsilon square edges uniformly at random. That you can do, you take your sketch, you solve the densest subgraph problem on this sample, and then you get a 1 plus epsilon approximation. That's the idea of the algorithm for the streaming densest subgraph problem. What I would like to say is the benefits that we get in the context of the k-clique densest subgraph problem. So if you think, as I said, you keep 6 n log n over epsilon square edges uniformly at random, or you can think of it as tossing one coin with probability p, 6 n log n divided by the number of hyperedges divided by epsilon square for every hyperedge. So you toss a coin, and you decide if you keep the edge or not. The expected space reduction in this case is 1 over p, where p is a sampling probability, and the speed up, assuming state-of-the-art maximum flow algorithm due to James or Lin, is 1 over p squared. So what we observe in practice is that as we increase k, the average speedups goes from 3 up to 24,000, and actually for k equals 5, there exist many data sets for which we could not solve the exact version of the algorithm, so we could only run the approximate. And the accuracy tends to increase because we have so many small k-cliques that somehow we go from accuracies 95% to close 100% accuracies. You can see that the speed up for k equals 2 is really small, and this is expected. Why? Because real-world networks typically are sparse to begin with, okay? So you cannot sparsify too much. So here is zooming in on a specific data set. You can find many more plots and results in our paper. So I have 4 plots. The x-axis is parameter k, and here you can see the H density. For every value of k, I do 5 experiments because it's a randomized algorithm. And you can see the H density increases. It's pretty well concentrated. The output size decreases, is what we observed also before. The accuracy, because we could solve the exact version here, is always lower bounded by 95% and gets closer to 1. And the speed up goes from roughly 4.6 times to roughly 2,000 times as we increase from k equals 2 to k equals 5. So let me conclude the presentation of our results by discussing dynamic networks. So the model here is very similar to the streaming model that I described earlier, but it cares about different aspects. So again, you have a graph that changes over time. You can have edge insertions and edge deletions. So you can see here a graph. You have one edge inserted here. You have one edge deleted here, and so on. So you have, again, a stream of updates. But the model cares about the update time. That is the amount of time you need to spend to update your data structures. You care about query time. So at any point in time, the user may ask you, give me the optimal density. And you want to be able to answer this query really fast. And it cares about approximation guarantees. So for the densest subgraph problem, no result was known before our stock paper. We showed that there exists a dynamic 4 plus epsilon approximation algorithm that uses linear space, constant query time, and polylog n update time. So every time some insertion or deletion takes place, we need polylog n update time to change our data structures. So an open problem is trying to improve this approximation guarantee. So I promised you a new line of research for graph analytics. So what we asked ourselves was, you have these 2 different models, the dynamic graph model and the streaming model, which have to do with the same type of input, but they care about different aspects. So if you remember, the streaming model cares a lot about space. It has n polylog n space, okay? So we were able to combine the best of both worlds into a single result. So we were able to show an algorithm that performs a single pass, achieves constant query time, gives 4 plus epsilon approximation, polylog n update time per update, and uses n polylog n space. So this is the first result, at least to our knowledge, of this type that combines streaming and dynamic. And an obvious direction is, can we come up with similar results for other type of objectives, like matchings, for instance? So I would like to conclude my presentation with a few research directions. So here we saw that by taking into account motifs, triangles, K4s and K5s, we were able to attack a very hard problem in practice, which is the problem of finding large near-cliques in large-scale data sets. So as David presented earlier, the idea of using motifs can give unique insights into the community structure of a graph. So actually, independently from David's work, we also introduced the notion of motifs within detection of communities. There is an archive paper online where we introduce a notion of a triangle expander or motif-based expander, and we actually have some of the same algorithmic results with David and his collaborators. And this is joint work with Jakub and Michael. And one other direction that I'm currently working on with collaborators from Japan is developing queries for graph databases where you have essentially heterogeneous networks where edges have possibly different types, and you want to find dense subgraphs which, let's say, contain many red and green edges but exclude blue edges, for instance. So this turns out to be something important in other applications. And I would like to thank you for your attention.